Okay, hello, welcome back to AMT 151 Basic Electricity. Give me a minute to get these slides set up on the screen. Please type in the chat if you can hear me. Okay, looks like somebody can hear me. Thank you. Give me just a second, I'm going to set this stuff up on the screen. Okay, so today we are going to be talking about impedance. The slides are pretty short, but don't misinterpret that this stuff needs to be studied and practiced. I included a YouTube video that has further examples of impedance and practice problems that you guys I would highly recommend doing. And definitely reading the text and practicing these things on your own, because it's not complicated, it just can be confusing with all of the formulas that are in your heads now going through DC and AC circuits. Okay, so the most important part is you're going to get the formulas. I'm going to provide them to you on the final, but you need to know how to use the formulas correctly. Okay, so the slides will be brief today, but you need to be practicing this stuff on your own in order to be competent enough to pass the final, especially, and then also to understand this stuff, even just at a basic level. So, let me think, any other announcements I have? I do want to mention that on Canvas, I posted an announcement about Thanksgiving. So this class does not meet on Thanksgiving, but we do meet the Wednesday before. So I'm going to bring up the announcement. What I've decided to do for that Wednesday. The campus is closed for the holiday on Thursday, November 26th through Sunday, November 29th. So that still means we are meeting for class on Wednesday, the 25th. What I'm doing is that I will be holding a lecture and you will have a quiz, but I'm going to give you an extended period of time to complete those. So my lecture will be posted by 10 a.m. on Wednesday the 25th, and so will the quiz. And then you will have until midnight of Wednesday to complete it. I know that the holiday can be kind of, there's a lot going on. So if people are traveling, getting ready for family or whatever, I am going to just give you guys a little bit of flexibility with that since it's the day before. Okay, and then I think I also posted, I might have already mentioned this, but I also posted an announcement about our final and the dates for the final. I think I did mention this in the last lecture. Okay, so make sure you guys are paying attention to the announcements. I posted the date for the final. I posted that I'll be doing a review on December 2nd. Okay, and I'm going to do a more in-depth review than I usually do, like with our midterm and stuff, because this class is really heavy on the formulas and math equations. I'm also going to give you guys a practice packet for you guys to practice some of these problems. That won't be due. It'll just be something to help you guys. So I highly recommend completing that when that is available. I gotta kind of figure out how I'm gonna get it to you guys electronically, but I'll figure that out. Okay, so a lot of information going on toward the end of this semester. Just make sure you're checking Canvas and keeping up with your reading material and definitely practicing these electrical equations, okay? So first we're going to talk about some AC formulas review. I'm going to review a couple of those that we've gone over, but I want to make sure you guys keep those fresh in your mind. We'll talk about impedance in series AC circuits, and we'll talk about impedance in parallel AC circuits. We actually will not talk about power factor calculations today. I'm going to do some more on that in the next lecture. Okay, so starting with some formula reviews that we've done, I want you guys to remember inductive reactance formula, inductive reactance being represented by XL. So if you are asked to find the inductive reactance of a circuit with certain values, remember that this is the formula you're going to use. You don't have to memorize the formula. The formula is going to be provided, but you do need to know how to use the correct formula and what values to plug in where. So inductive reactance equals 2 pi times your frequency times your inductance of that circuit, whatever circuit it's being applied to, okay? Capacitive reactance. Your capacitive reactance is 1 over 2 pi times your frequency times capacitance. Okay, so I just want to review those two formulas. And sorry, my dogs are playing in the background. I don't know if you can hear that. But those are things that are going to be on your final. You guys are going to need to know how to apply those equations. So impedance. AC circuits contain capacitive reactance and inductive reactance that are accounted for in determination of total current. The combination of resistance, capacitive reactance, and inductive reactance is called impedance. Hang on, I'm going to turn the sound up for a minute so I can move locations. Okay, hopefully that's a little better. The combination of resistance, capacitive reactance, and inductive reactance is called impedance, okay? The formula symbol for impedance is Z. Capacitive reactance and inductive reactance have opposite effects in an AC circuit. So to find the total reactance, we use the difference in the reactances of capacitive reactance and inductive reactance. So we will consider inductive reactance as positive. We do this because inductive reactance causes the voltage to lead the current. Capacitive reactance is considered negative because it causes the voltage to lag. So what we're going to do to find total reactance of an AC circuit is add the two together and we'll get total reactance. And here's your equation for that. Our total reactance here, XT, is given by XL, our inductive reactance, plus our capacitive reactance, which is considered negative. Resistance in a circuit does not cause the current to lead or lag. The effect is 90 degrees ahead of the inductance and 90 degrees behind capacitance. Resistance and reactance must be added vectorially. I'm not going to get too in-depth about the vector equations because it's not relative to us. What is relative to us in this class as far as being AMTs and what the FAA wants you to know is the formulas and how to use the formulas, okay? So a vector is a quantity having both magnitude and direction. Vectors are often represented graphically by a line pointing in a given direction. This vector stuff gets more into trigonometry than we need to for the scope of this class. So that's kind of just for your information, for background information on the formula. This information is just telling you how this formula kind of was made, okay? So using vector addition, the three vectors, which are inductive reactance, capacitive reactance, and resistance, can be combined into one resultant vector called impedance. Okay, so if you're confused by the vectors, don't worry about it. This is just background information for the formula. And here's our formula. So this formula is typically used to solve for Z, which is our impedance, or an unknown R, which is our resistance, or an X value, which can either be our inductive reactance or our inductive capacitance, okay? This formula can be applied to determine the impedance in series circuits only. So the formula above is used when you are looking for the impedance of series circuits only, AC series circuits only. And this formula reads as our impedance of a series circuit, of an RLC series circuit, which just means resistance, inductance, capacitance. Otherwise can also be called the impedance of an AC series circuit, is equal to the square root of our resistance squared plus our inductive reactance minus our capacitive reactance squared, okay? A further step of this is if we are asked to find the current of this AC series circuit. So after the impedance is found, after we've applied that formula and plugged in our findings, our values, other values can be found by using Ohm's law for AC circuits, okay? And Ohm's law for AC circuits is current equals voltage over impedance. If you remember, Ohm's law for DC circuits is very similar. It's current over voltage equals current equals voltage over resistance. Okay, so E over R. Remember, capital E is used to represent voltage in this Ohm's law equation. Okay, so you can even use a V if that is easier for you to compute. But capital E is only used as a symbol in the Ohm's law. So Ohm's law in AC circuits, current equals voltage over impedance. Sample problem. So an example of this is if a series AC circuit, remember that formula that we're talking about is applicable only in series AC circuits. So a series AC circuit contains an inductor with, so it's giving you values for your inductive reactance, which is XL. So we have 12 ohms. Capacitive reactance, which is XC. We have 18 ohms. And our resistance is 5 ohms. Our applied voltage is 120 volts AC. Now, we want to find the current flow. Okay? Step 1. So this is just a note up here. Remember, Ohm's law in AC circuits equals current equals voltage over impedance. But we're going to take these values, and our step 1 is first we want to find the value for Z, our impedance. Okay? So here's our formula again. Impedance equals the square root of resistance squared plus inductive reactance minus capacitive reactance squared. Okay. We were given the values for our resistance. We were given the values for our inductive reactance and our capacitive reactance. So all of that work was done for us. But remember, if you are not given the value, say you're not given the value of inductive reactance, we have a formula to find the inductive reactance. Okay, so all of this stuff is kind of building on each other. Remember, our formula for inductive reactance was 2 pi times your frequency times your inductance. Okay, so that would come from, those values would come from your circuit. Once you attain those values, that value that you get from that equation can be plugged into the impedance equation. Okay, so this is why I'm saying these are a lot of steps that build on each other, so you guys need to be practicing this outside of class or outside of lecture. Okay, so just a note, our inductive reactance minus our inductive capacitance may produce a negative number in some cases. Not all cases, but sometimes it does. Not to worry, because this negative number will become positive when it is squared. In the impedance equation, we square the inductive reactance minus the capacitive reactance. So whatever number we get is going to be squared. If it's negative, it's going to become a positive. Okay, so we were given our values, and here is our formula. We were told that our resistance is 5 ohms. We were also told that our inductive reactance of our inductor was 12 ohms, and our capacitive reactance was 18 ohms. This information was all given to us in the beginning of the problem, okay? So now I've plugged them in here to our equation. And this square root is a square root of the entire problem. When I'm typing in my slides, I have no idea how to get this square root to extend all the way over. So hopefully that's not too confusing. That's why I included this, the formula up here, because we're not just square rooting the 5, we're square rooting the whole problem. I probably just confused you guys, but this is more correct than this. I just have no way of really typing that I know of. Okay, so we plugged in our values. The first thing we're going to do, just like we've learned in, grade school math, is we're going to do everything inside the parentheses. 12 minus 18 actually gives us -6, okay? But we are going to square that, which gives us 36. And 5 squared gives us 25. Now, we have not done the square root of anything, that's last. But if we add 25 and 36 and square root that, we're going to get 7.8 ohms. Impedance is measured in ohms, okay? So the math is very simple. Look, there's 3 steps, but making sure you have all the right information, knowing what these equations mean, what the symbols mean. If you don't know that, then it's going to be impossible to figure out these equations, okay? Step 2, remember, we're not done. We found the impedance, but our original problem asked us to find the current of the circuit. So we have to do all of that first so that we can find Z, okay? Because the voltage was given to us. So just like in algebra, we have to have 2 of these variables in order to solve for the other, right? So we found our impedance. Voltage was given to us. We have 120 volts AC. Our impedance we calculated as 7.8 ohms. And so now we're just going to divide 120 volts over 7.8 ohms gives us a current of 15.4 amps. Okay? So simple enough, you just got to keep all the information straight. Just a side note, in that particular equation, current will lead voltage in that circuit because the capacitive reactance was larger than the inductive reactance. And remember, we said capacitive reactance is considered negative, and the inductive reactance is considered positive. So when this is larger, the current will lead the voltage. When your inductive reactance is larger, then the current will lag the voltage. Okay, impedance in parallel. So if you read over here on my slide, this information is not testable. There is nothing, for some reason, the FAA doesn't require you to know in the impedance formula in parallel. There are no questions asked of you to solve for impedance in parallel. So you don't need to know any of this. This is just like 2 slides for information, because in every other area we've covered series and parallel circuits. So this is for your information only. We went through series circuits. The FAA does have problems that they ask you to solve for in AC series circuits as far as impedance, but they do not have any in parallel as far as impedance. So just for your information, this will not be on any test or quiz. Impedance in parallel calculations used to find the impedance in parallel circuits are different from those used with series circuits. This is your equation, find impedance in parallel. The equation is simply the inverse of the resistance, the inductive reactance, and the capacitive reactance for a given circuit. So you'll see here we have 1 over our total impedance in a parallel circuit, AC circuit, equals 1 over our resistance squared plus 1 over our inductive reactance minus 1 over our capacitive reactance squared, and the square root of all of that. So similar to many of our other equations, impedance in parallel is found this way. Again, you don't need to memorize that formula. That formula will not even be provided to you on the test, because there will not be any questions on the test about impedance in parallel. Okay, so that's it. But I know that might seem short. I'm sure you guys don't care. But there's a lot of information and a lot of practicing that needs to happen in order to be somewhat proficient at that. So if you guys don't have any questions, that completes the slides for today. Your quiz will be available at 6 p.m. and I will see you guys for lecture on Monday. Okay? There's also that video that I attached. I attached 2 videos to the announcement and the lecture. Another one with more examples on impedance, and another one that's review of AC circuits in general. These slides will be available for you tomorrow. They'll be posted on Canvas. Okay.